Hello everyone, welcome to another programming session with Scilab on digital signal processing. So today's lab we are going to talk about a fast Fourier transform algorithm FFT method known as your decimation in time algorithm. So for those who are not familiar with what decimation in time algorithm does, I strongly suggest you go back to our lectures on DIT algorithm and then get familiar with the steps in order to understand this program. So just to summarize, I'll just show the slide that contains the steps of your DIT butterfly diagram. So basically in today's class, I'm going to write the program for this structure that is shown here. So I start with, this is my input sequence, which is structured from 0 to 7 in this order, 0, 4, 2, 6, 1, 5, 3, 7. And then I call this as my stage 1. So where I'm taking these values, I'm taking these two values and adding them and subtracting them with a twiddle factor of W80. So all the derivative steps have been discussed prior to this slide. So watching that lecture might help you if you are not familiar with this DIT algorithm. And then coming to stage 2, the output of my stage 1 is taken as the input for my stage 2, and then I get my W80, W82 as the twiddle multiple, and then that is the output of stage 2. Then that is the input for my stage 3, where I use 4 twiddle factors or the linear transformation multiple W80, W81, W82, and W83. Good. So now we are going to see the program. No, it's an 8-point radix2 DIT FFT, and that is what this program here is going to do. So it's going to do our 8-point radix2 DIT FFT butterfly diagram. Good. So let's get started with this program here. Okay, that is the intro for you. And now the Scilab function which is readily available and which will do this for me is your FFT of X. So if I just use this FFT on my input signal X, I get the fast Fourier transform done. But I don't know what method is used internally or in your Scilab, because there are two ways to do this, which we have discussed in our lectures. One method is decimation in time. The other one is your decimation in frequency. So we are going to see both the programs today. So the starting is I am taking your input sequence, which we have solved this sequence in your class problem. So this is one of your class problem, right? So input sequence, or just I'll adjust my typing, yeah, keyboard, and now it's good. All right, so that is your input sequence. It is a 8-point input sequence, 1100 1100. And then what is the first step? So my first step here is I have to restructure the input. So my input is not in sequence. So it is from 0 to 7. So I need to restructure it. And the program that allows, in Scilab, there is no direct command for restructuring, because in my MATLAB I was having this command bit reverse order, and I do that, and it is going to take this input and restructure it in this order for me, right? It's going to do it automatically, but here I don't have an automated way to do this in Scilab, or at least I couldn't find any when I was preparing this code. So what I'm doing is I'm just taking this n equal to, these are the index that I want, 04261537. So if I see this 04, so let me just zoom in on this one, 04261537. So I have written that here, and since my Scilab indexing starts from 1, so there is no 0 index in both Scilab and MATLAB. So since my indexing starts from 1, I am doing this plus 1. So this plus 1 is done because your Scilab don't do your 0 indexing. All right, good, because it starts from 1, and that is done. And now I'm coming to the restructuring. So these are the index. So what I'm going to do is I'm going to resequence. I'm going to rearrange my input in this order. That is, my order is given by n of I. So what I'm going to first take is s is equal to n of I. So the first term will be 0 plus 1, 1. and the first term, it's going to take x of 1, and x of 1 is your first term. Good. And the next, it's going to take 4 plus 1, 5. So after the first term, it's going to go to the fifth term. So it's going to take the fifth term and put it in my x of n. And then after that, it's going to take the 2 plus 1, third term, 6 plus 1, seventh term. So it's going to do it in this order. It's going to take the values in these places and put it in sequence. And that is how I'm getting my restructuring done here. So here your x of n is the input which is restructured for your DIT FFT, meaning that is this form 04261537. So that takes care of the restructuring, right? So that takes care of the restructuring of your input. And now we go to our stages 1 to 3. So we are seeing, we have 3 stages. So we are going to see those 3 stages now. So my first stage is this. So what I have here, this is my first stage. And in order to do this stage, I'm taking my O to be x of n. So I'm just substitution of variable. Then my n is equal to length of x, where x is equal to 8. Okay, n is equal to 8. Good. So that is the length of my x. And then I have my number of stages, which is log 2n. So these are the formulas directly out of this FFT textbook. So the number of stages is going to be given as 3, because for 8 point it's going to be log 2 8, and that is going to be 3. So that is what we are basically finding out here. So when I have this, log 2 8 is equal to 3. So the number of stages is S is equal to 3. So I have 3 stages, and then this is my first stage. And what do I have at my first stage? I needed these. No, I needed plus W80 and minus W80. That is what I've written here. And then I'm going to set a counter for my stage, and that is how, because there is a indexing you have to do for your output. So my output is indexed with this count. So it's like it's incremented sequentially. Count is 1. So this becomes 1, 1 plus 1, 2. Then count is incremented to 1 plus 2, 3. So next time it becomes 3 and 4, then 5 and 6, and 7 and 8. So this is your output that is coming out of this end. And this is the formula that I'm going to apply. On plus On plus 1. So here if you see x0 plus x4. So here this is O, and this is written as On plus On plus 1 into W80. So I am showing this. So it takes your first element and your second element and add it, and then it subtracts it. So that is exactly what is happening here. If you take away the index, because now we have rearranged the index, it's taking these two, the first two elements, right? So these, if you see these two dots, these are the first two elements, and it is adding them, and then it is subtracting them. Adding them, subtracting them, adding them, subtracting them. And that is what exactly these two lines take care of. Good. So that is done for your stage 1. And now for my stage 2, all I need is the output of my stage 1, which is this variable f. So I'm going to use this f. I'm going to take this f, and then I'm going to go to my next stage, stage 2, where I'm using two twiddles, 80 and 82. And now my grouping, if you see this blobs, the grouping is between every alternate terms. So I'm grouping the first and third, second and fourth. Right, I'm coming to 5th and 7th and 6th and 8th. So the grouping is between every alternate term, and that is exactly what I'm going to do in my stage 2. So I've set the counter for 1. Then my n is equal to 1 is to 4 is to n minus 1, because I'm doing this in two groups. And W80 and W82 is given as this. So I'm computing this from the formula. So what is the twiddle formula, right? I didn't mention it. Yeah, I mentioned it in my FFT program, sorry, in my DFT program. So your W8 is nothing but e to the power of minus 2 pi j by n, right? And 8 underscore 0 means your n is 0. Here this is 0 and 2. So you have n equal to 0 and 2. Okay, good. So that is your twiddle factor. And now I'm taking these values g count plus 2, and that is going to be your sum and difference with 0. Then for the next one, it's going to be W82. So W80 sum and difference and W82 sum and difference. And that is what your stage 2 does. So stage 2, if I put these values, if I plug in the values for my, this is still the first stage, then I get G1 and G3. So here count is 1 and 3. F1 plus F3. So every other term means the first term and the third term, then second term and the fourth term. And then I increment the count to 1 plus 4 and then I get the second. So you can just plug in these values and you can write this down. I've shown some examples here. I've just shown one example on how this loop will turn out to be. All right, good. So now coming to our final stage, now I'm having 4 twiddle factors, so I'm computing these 4. So you don't have, this is not a very optimized code because I'm repeating many lines here. So, but it is mainly for, imparting teaching and learning. So the learning, will be easier if I do it in this manner. So for my stage 3, I'm again setting the counter. It's like I'm resetting the counter every time to 1 just before each stage. And then my W8 is now given to be e to the power of this. Good. And now I'm just putting it here n minus 1 because here I'm having 0, 1, 2, 3, and that is going to be taken from this n. So n will be from 1 to n by 8, so that is 4. So here it's going to be like 1 minus 1, that is 0, 2 minus 1, 1, 3 minus 1, 2, and 4 minus 1, 3. So this n minus 1 takes care that I get all the 4 twiddle factors, and then I'm doing this plus and minus each time. So I'm running this loop for 4 times. Good. And that is how, that is the output you will be getting now. So if I run this code, let us run this code. I run it. Now let me just go. Okay. Once again, what I want to show is I have done this numerical in the class. So let me see if I have it here. If not, I will be having it in my next slide. Oh yeah, I have it here. Good. So this was a question that I have done in my lecture videos. So 1 1. So if you see, the question is 1 1 0 0 1 1 0 0, and that is the sequence that I have here. So here my input is also 1 1 0 0 1 1 0 0. So now let's see what are the each stage output. So let's go to our Scilab. So let's take this Scilab command workspace I have here. So in this workspace, I'm going to check what is my first stage output. So my first stage output here is 20002000. So my first stage output is my variable f, right? So I'm opening this, see, and then I'm comparing it with this. So if I compare this and this, you see the values are the same. Good. And what about the second stage? 20202020. So second stage output is G, and then if I take this output, I am again getting it as 202020. See, it's matching my second stage, and my last stage, final stage output is this. So let's go to our final output, capital X, and then if I take this capital X, you see it's again matching. 402 minus 2i 0002 plus 2i. Done. So that is how you do your DFT, right? Sorry, your FFT using the Scilab code. I can always check with this y equal to FFT of x. So here I have my y, which is done using an inbuilt function. And again, okay, I just have to take the transpose of this, but it is pretty much the same. 402 minus 2i 0002 plus 2i 0. The same answer I'm getting here. Good. So this is your DIT FFT which you are seeing in your class. And now let me quickly, what we are going to do is we are going to see one more program for today because there are two methods for your FFT. So this is your second method for FFT. That is your DIF algorithm. So your decimation in frequency algorithm, let us just go over this decimation in frequency algorithm. I have the PPT slide right here. So I'll just get to the structure of it. So what is different in DIF is DIF is basically a flipped version of your DIT. So I don't what I will say is, if you see the stages here, they are going to be slightly different. So since it's a flipped version, your first stage is gonna have W80, 1, 2, 3. Your second stage is gonna have W80, and your third stage is gonna have just W80 because it's now flipped. In contrast to your DIT. And another thing, very important thing is here. If you see the twiddle multiple, this flipping, make sure that the twiddle multiples or the linear transformation multiples come outside the branch. So when they are outside the branch, they don't have any participation in this sum of values, and they multiply with the difference of values on the whole. So how your twiddle operates on the sum of values and the difference of values is quite different when compared to our DIT. So in your DIT algorithm, for both the sum of values and the difference of values, you have this thing, no, you have this twiddle operating because it was plus W minus W, right? And it was multiplying with the second value each time. But here, no, if you see in DIF, for the sum of values, there is no twiddle. And for the difference of values, your twiddle is after you take the difference. So you finish the difference because once you when you do the flipping, your twiddle becomes outside the branch. It is no longer it's no longer part of the branch. So which means you take the difference, and then after you take the difference, you multiply with your twiddle. Good, I've shown that example here how it becomes. Yeah, so this is the diagram that I want to show on the right hand side. So this flipping, this is the DIT where your W80 is before the branch, which means it participates in both the branch computations. Right, so if I take this diagonal intersection lines as my branches, your W80 participate in both the calculations. But whereas when I flip this for my DIF, what happens is my W80 comes to this side because of the flipping, and it's clearly now outside the branch computation because when I do this branch calculation, I'm no longer bothered about this W80. So that is why you get this term as E minus F W80. Good, because whereas on the DIT you get this to be A plus W80B and A minus W80B, and here for DIF you get it as E minus F W80. So this is the difference between your DIT and DIF. Again, like I said, you want more insight into this, please watch the lecture videos because this is a practical video. So I'm going to do the DIF FFT for this, radix 2 DIT FFT, DIF FFT for the same input sequence. Good, and I'm going to show you what happens here. So this is my input, and then I'm taking log 2 of length of x, right? I can write it in 2 line. I'll write it in this manner: n equal to length of x, and the number of stages is given by log 2 of n. This is your number of stages. So here also you're going to have 2 stage. Okay, I've done this again, so no need to repeat this. I'll just put it here. Good, done. Now I'm coming for my stage 1. So most of the things are the stage same. So what I've done is I've copied my DIT program and I've made some changes here. So for the first stage, my stage 3 code is going to come here. For the first stage, I'm having all 4 twiddle factors, which means I'm going to be using W8 to the power n minus 1. And then if you see here, my sum of value is independent of the twiddle, and only the difference of value is whole multiplied by twiddle, as I just explained in this slide. Good. So how I explained here, this is basically why we are not, why the sum of value is not having any twiddle, and the difference E plus F, it is as it is, and E minus F W80. That is exactly what I'm showing here. So this is my stage 1 for my DIF. Coming to my stage 2, pretty much most of the code is the same. I've just removed the twiddles in the first sum of value in each of these, and then kept it as a different, it is mine after the difference of value I multiply with this W80 and W82, and that is your DIF, and then I do for my stage 3. So if you see, if you look closely, your stage 3, it is just this code, what I have here, it's a flip. DIF is obtained by flipping your DIT, right? Flipping on the center. So how do you flip? Right to left or left to right? It's probably the output to the input. Right, so we are doing it. So the decimation, the saying is the DIT decimation starts at the input, the DIF decimation starts from the output. That is one way to explain things. And now what happens is your output needs to be restructured, because here on the input I am DIF, I am not doing any restructuring, right? We have not done that restructuring where we arrange it in this manner 04261537. So we are not done this, but which means your output is going to be now not in sequence. So I have to restructure my output, and I'm doing the same restructuring logic I have used in the DIT, and then I get my output to be Y. Good. So let me run this program for you, and then let's go to our Scilab workspace and see the outputs. So what are the outputs that I'm getting here? So let us quickly see what do I have here for a numerical. Yes. So this is my numerical. I have used 110011, the same question. So my first stage in my DIF should give me 22000 or 0. So let's see what is the first stage output of my program. So in my first stage, my output is G. So let us see what I have for G. Okay, so G is the same, C220000. So this is the program, and for stage 2, I am having this. So let's see what is the stage 2 variable. I think it is F. Yes, stage 2 variable is F. So which means for F, I am getting this 222 minus 2i. So this is e to the power of minus 16. So that is almost the same. So this is correct. 222. This is like very small value. Just I can write it as minus 2i. It is the same. 222 minus 2i 00. That is correct. Then coming to my third stage, which will be not structured, it will be 40 this. So let's come to our third stage. Our third stage output is at my XF. So my third stage is XF. I'm opening this. Let me click this, and then what do I have? Yeah, 402 minus 2i. Good. It is again same 40. No, where is it? 402 minus 2i, 2 plus 2j 000. Exactly the same. So this is what? It is in not sequence 04261537. So which means we are doing the sequencing next. So after I get my XF, I apply the sequencing and I get my Y. So that is the final output. So let me take my Y here, and I get the Y to be 402 minus 2j 0002 plus 2j 0. Good. So this is how you do this DIF program. Done. So that is your DIF program, and the first one was your DIT butterfly program in Scilab. Okay, so thank you.